Swayam Prabha. Digital India. Educated India.
They are in general, yeah. So, a Cn followed by a sigma perpendicular to Cn, which we write by a sigma h, calling as horizontal. That is, if the line is vertical, the sigma is called horizontal. Okay. This is written as Sn. This is the other molecular symmetry element. Okay. Okay, now, is here we have a C4 followed by a sigma h, so we call this as S4. What about C2 followed by a sigma h? Sigma is the plane perpendicular to the line. Okay, so Cn is the axis, sigma is the line perpendicular, the plane perpendicular to. Will C2 sigma h be an element? For this? Because you see, C2 takes a molecule to identical configuration already. Now you do a sigma h, it's going to displace all the atoms. Because the atoms which are here, the other two atoms which are on this side, they will get reflected into the vacant positions. And so the molecule is not the same. Therefore, this is not an element. Okay. But C2 is an element. This molecule doesn't have sigma h, there is no sigma h, there is no plane perpendicular, or you see there is no plane like this, there is no plane like this. You can see that the plane is the one that contains any of the two bonds. Any of the two bonds, that's this one. It's already there. Because the plane that contains any of the two bonds, sigma, obviously will reflect, see, this diagonal plane will reflect these two atoms. This diagonal plane will reflect these two atoms. Okay. If you have a plane which is through this, that will reflect these two atoms. So those sigmas are already there. This is a special one. This is a plane which is perpendicular to your rotation axis. It doesn't exist. But if you say 90 degrees, how many such elements are there? Each rotation axis, yes, C4, C2 will have a C4, will have an S4. So there are three of them. Okay, so are we finished with them? Or do we have anything more? What are they? Yeah? No. But if you give an answer, you should also know why. What are they? Okay, what is special about 90 degrees? What about minus 90 degrees? If you rotate the other way around.
Sir, is it not the same as rotating as 270 degrees?
That's what I'm saying, yes. Will it work?
Yeah, it should.
Is it a different element? Yes, it is. Yes, it is. You see, you do a 90 degree, 1 and 2, let's do that. You draw the picture, okay? We have now labeled the atoms. Okay? We have 1, we have 2, we have 3, and we have 4. So when you do the 90 sigma h, what do you get? When you do, what do you get? The 2 goes here. If you do, if the rotation is this way, okay? You can choose whichever way, this way or that way, right-handed or left-handed. So, where does 1 go now? S4. S4. 1 goes here and then it gets reflected to 4. So, this is 1. Okay, after the S4. Where are the other atoms? 3 goes to 2. So this is 3, yes. And so this is 2, and this is 4. Now let us do a 270 degree operation. Do a 270 degree operation. We start with the same thing, 1, 3, 2, and 4. Tell me where it is after the S4. Yes, 4, 3. Yeah. So let me draw the picture, then you can tell me where it is. Yeah, now you tell me. 1 goes to? Okay. So 1 goes to 2? Okay, so this is 1. 3 goes to 4. So this is 3. 2. Okay, so this is 4. This is 2. Are they the same? If the atoms are labeled, somehow I put a label on the atoms. Is that picture the same as that picture? The molecules are identical. Yes, because all the hydrogen atoms are indistinguishable. All the chlorine atoms are indistinguishable. See CX4. But the point is the operations are mathematically different if you label them. This outcome of this operation is not the same as the outcome of this operation. Okay? It's because they are identical, they are symmetry operations. But if you label them and if you represent the atoms by some identity, you see that you get identical configurations but not identical placements of the atoms. They differ. Therefore, S4 is an element, S4-3 is another element. How many S4-3? 3. 3. 3 axes, 3 S4s.
For minus 90. Yeah. For 270.
There are 3 S4 SC4 axes. So you have a 90 degree rotation or a 270 degree. So there are totally 6. So let us count them. E, 8C3, 6 sigma, 3C2, and let me write 3C2 first, 6 sigma, and 6S4. What is the total? 24. 24. Okay, only one more element that the molecule has to have as a symmetry, which is the inversion symmetry. That is the molecule in 3 dimensions. If you take the atom, any atom, you call that as XYZ coordinate in 3-dimensional coordinate. If you put the atom to minus X, minus Y, minus Z, invert the coordinates. If there is an identical atom there, and this goes there, then that's called the inversion. So, example is this. So, 3, for example, if you have the axis system this way, so 3 has some coordinates, X, Y, Z. Its inversion will be here. Okay, minus X, minus Y, minus Z. But that's not an element of symmetry here because there's no atom here. Okay, it's not there. Therefore, I is not present here. On the other hand, suppose I give you a molecule, again on the cube, it's easier to deal with the cubes. I have a molecule which is connected to the 6 points on the plane. Body center. What do we call this molecule if we connect all these things? Sorry?
Body center.
No, it's octahedral. The shape will be octahedral. Shape will be octahedral. Okay? Now you see, if you take this point X, Y, Z, what is its minus X, minus Y, minus Z? That's this one. There is an identical atom. Therefore, if you invert the coordinates of these 2 atoms, they go into each other. But that's not true for only this. This is for every pair of identical atoms. These two. So you can see that that's called simultaneously inverting all the coordinates of the atom. in an axis system. Put an axis system in mind. So that's called the inversion. This completes the total elements of symmetry that we know at one level of molecular structure.
So like always the center, like origin should be taken at the center of this cube.
Usually at the center of symmetry of the molecule. Yeah. You put the
When you say in this case there's no center of symmetry, that's
carbon. Center of symmetry in the sense a center of mass.
oh,
CH4, carbon is a center of mass. Okay. So you put the
there's no center of symmetry.
no, there's no center of symmetry. That's right. That's right. No, it's be careful. Center of symmetry is reference to the some of the properties of the atoms. This, for example, if you think about it, if this is a dipole, carbon is a positive. If it is chlorine, it's a dipole. Okay. Now, this is another dipole. This is another dipole. This is another one. What is the sum of all four? 0. So it is a center of symmetry. It's not center of inversion symmetry.
But for center of symmetry to exist, like if about that point you exactly reflect it, then
No.
it should
Yeah, see, what I mean, yeah, it's very clear. It's called the inversion center.
that is the inversion.
That point is called the inversion center, but this molecule does not have an inversion center. This has an inversion center.
This is the inversion center.
This has an inversion center.
Center of the oxygen.
That's right. This is the origin. With respect to that, this is the positive side of the coordinate, this is the negative side, and you see both of them. Yeah.
What is the center of symmetry?
Okay, center of symmetry, when you talk about with respect to molecular systems, usually you refer to the properties like the dipole moment or the electric quadrupole moment or the others. And then if the molecule has a very, symmetric structure, the center of mass, for example, in the case of CX4, carbon is the center of mass. On the other hand, if you say CH3Cl, the center of mass is not on the carbon, it's on the CCl bond. That molecule doesn't have a center of symmetry.
Okay, because it isn't symmetrical.
It only has, see, center of mass is there for any molecule. It's basically the mass point about which all the masses are evenly distributed, Mi times Xi, Ri, if you, that should be, the sum of that should be 0. Okay? Usually that's the center of symmetry. Okay?
In this case, it's
In this case, carbon is still the center of symmetry, but it's not the center of inversion symmetry.
what is the center of symmetry?
No, center of, see, with respect to molecular properties we discussed.
Symmetry is the center of mass.
Yeah, you can do that for wherever the dipole, see, in the case of methane, if you think about it, there is no dipole. In the case of
We can
carbon,
think, right? There is we can consider hydrogen to be more electropositive than
there's no, yeah, even then you add, hydrogen is more electronegative.
net dipole moment is 0.
Delta, all I'm saying is that, is there a dipole, net dipole moment for the molecule? Therefore, that point is called the center of symmetry. In terms of structure, in terms of structures. Molecular structures, it's the center of symmetry exists if the molecule has 0 dipole. Carbon dioxide, for example. The CO, both the bonds, okay, cancel each other. Water. Does water have a center of symmetry? It has a dipole moment. Because you see HO, if you think about it, OH, the dipole is pointing this way, the dipole is pointing this way, the two vectors add up to give you that. So there's no, which one?
We'll add that.
You have to add the dipole.
Yeah, correct.
Yeah, you have to add the dipole. Therefore, there is no center of symmetry. So in spectroscopy, we always worry about these molecular properties and decide the center of symmetry as to whether these dipoles are exactly 0 or exactly not. Yeah.
Sir, but it seems like a misnomer to call it center of symmetry, right, sir? How does symmetry have to do with dipoles in this situation?
So carbon is the center of symmetry in this case because all axes, all planes do not change the carbon,
Okay.
do not move the carbon.
A point, okay.
There is one point in the molecule which does not move. Okay, that doesn't mean that in water oxygen is the center of symmetry. No, the oxygen doesn't move, but it's not a center of symmetry
Because there are all dipoles.
because there is electric properties on that. Okay, so your formal definition of center of symmetry with respect to static objects, you have to make sure that this is reference to the electrical properties that we do. Okay,
Okay.
yeah,
Understood.
yeah. Inversion symmetry is very different. ethylene. This is an I think all of you know that this is 120 degrees, right? CCH is 120 degrees. Now you can tell me that this is the center of symmetry. Okay. Exactly. It is also an inversion center.
Yes, sir.
Okay. With respect to this carbon is on the side. You can interchange the coordinates of these two carbons minus. They will go to each other. This hydrogen will go to here. This hydrogen will go to here. But if you have a Cl in the Cl, no inversion center. It is also not a center of symmetry. It is also not a center of symmetry. But if you have a chlorine here, does it have a center of symmetry? Why not? They are both the same. They are both the same. Both the center and the inversion center both are the same. Molecule doesn't have a dipole moment. Right? The dipole that points this way is cancelled by the dipole that points this way. The dipole that points this way is cancelled by the dipole that points this way. And this is an exact inversion center because this chlorine, when you change its coordinates from XYZ, if you think about the XYZ axis as perpendicular, okay, you see that this chlorine goes here and that comes here. This hydrogen go here. Therefore, you see, so clarity will come out when you start looking at inversion centers and the center of symmetry with respect to electrical properties and so on. This molecule also doesn't have a dipole moment. Okay. So, the idea here is that this is octahedron, this is tetrahedron. Where are we now? Okay, we should leave soon. Now, the interesting case of slightly two more difficult molecules I'll handle in the next class. Okay, it's 5:30 already. Okay, the two more handles is the one that I started with, C60, and the other is octahedron. You know, you have octahedral complexes in the 11th standard textbook or 12th standard textbook. Do you have them? In organic chemistry, yeah. Ligand. SF6 is one. Yes, that's a normal. It's a regular molecule. But the inorganic complexation, coordination chemistry is taught. Yes? That's in 12th. Okay, so you will see tetrahedral coordination complexes, octahedral coordination complexes, and so on. The structure octahedron will become important, but as you said, SF6 is already an octahedron. Likewise, there are other molecules. And the presence of these symmetry elements in our mental picture enables us to apply a branch of mathematics which beautifully morphs with these symmetry elements to study the molecular properties, to predict the behavior of the atoms, to understand why molecules behave this way, that way, etc. So this is one aspect of chemistry where physics, mathematics, and the sheer thought experience gives us tools to study them. Yeah.
So is SN called the alternation?
It's called?
Alternation axis.
No, I didn't hear, sorry.
Is SN
Yeah.
the rotation and
Yeah.
the flipping?
Yeah.
Is that called the alternation axis?
That is the alternating axis. Yeah, it is also known as the alternating axis. Yes, yeah, that's correct. A molecule which has an S2 symmetry, alternating axis symmetry, will not be optically active. Okay, so optical activity, the physical property that you can measure is associated with the molecular structure and the symmetry of the molecules. Isn't that beautiful?
So why is that?
Find out. We'll do more about it over a period of time. Yeah. You look at the charge fields and so on. It's easy to show that the optical activity essentially means they are mirror images which are not superimposable. But an object which has an S2 axis, the objects will be superimposable on the other. Yeah, exact mirror images will be superimposable on the other. The optical activity is due to non-superimposability of the mirror images. That is why I said CHClBri is an optically active compound. Its mirror image will not superimpose on that. But you put CHClBr, that's a difference that has a symmetry in it. The images will be superimposable. So SN axis confirms that these images are superimposable. Presence of the SN axis. Okay. S2, I think, or any SN axis if I remember. I should check that. Okay. So this is just an introduction to something which is very esoteric that you may not generally hear. The point is the topics that we talk about are things which connect multiple branches at the same time but give you clear outcomes in the study of chemistry or in the study of physics or in the study of mathematics. And in physics, symmetry plays a fundamental role, and the role of symmetry in quantum mechanics has led to many beautiful discoveries. In fact, you should know that the quark structure is considered to be known, is considered or is written as eightfold symmetry. Okay.
What's a
Quark, the structure of quark is associated with the eightfold symmetry. Talk to Professor Bala about that, okay? He will explain to you what is the eightfold symmetry in them. And then today we talk about the string theory and many other group theoretical methods in physics. They all have built themselves on the elements of symmetry which we perceive in terms of our ability to identify an axis, identify a plane. And solids, if you think about regular solids, they have, in addition to the symmetry on the location of the lattice, they also have a lattice translation symmetry. If you move the solid from the point from one lattice to an equivalent lattice translationally, you'll see that the solid, assuming that it's infinite dimensional, the solid looks to be the same. Therefore, the solid, in addition to the molecular systems which occupy the individual sites having their own symmetry, solid also has a translational symmetry. And that leads to, because it's three-dimensional now, translation plus this, that leads to what we call as the space groups for these solids. Space groups, SPACE, space groups for them. The molecules that we consider in isolation, one molecule, in all these things, there will be one point in the molecule or more than one point that will not be disturbed at all if you perform all the symmetry operations. In the case of water, it's the oxygen. In the case of methane, it's a carbon. This doesn't move. All the 24 operations stays where it is. There is one point, at least one point in the molecule or one line or a plane in the molecule that does not change. Therefore, the collection of these symmetry elements which form a mathematical structure called a group, the group is known as a point group, not as any other. The 24 elements of methane, they form a point group called a tetrahedral point group. The moment you go to octahedron, you will see that the symmetry is doubled. Octahedron will have 48 symmetry elements, not 24. And likewise, many other molecular systems. So when we try to understand molecular systems from the study of property, we see that mathematical tools completely unconnected with our thinking of molecules are very useful sometimes. Yeah.
Are these translational and rotational symmetries, are these the ones that are referred to when they talk about degrees of freedom?
No. The degrees of freedom refer to the energy component. The molecular energies.
But again, there also they talk about translation, rotational components.
No. When you talk about translational motion, it's associated with when you talk about the degrees of freedom, the translational degree of freedom refers to the three possible amounts of energy depending on the molecular motion in three mutually perpendicular directions. Rotational energy refers to the molecular rotational angular momentum multiplied by the moments of inertia square, angular velocity I omega square, that the omega is about the axis about which you declare the I for that. That's an energy component. So the degrees of freedom that you talk about refer to the total energy and how we can sort of consider these as components of energy. Okay?
So,
Yeah.
degrees of freedom, for example, for a linear molecule, A linear molecule doesn't have rotational degree of freedom across its
The reason for that is there is no energy change during that rotation because they are point masses.
Right. So
There's no moment of inertia.
So wouldn't that technically be considered some sort of continuous symmetry? Or something?
What is technically?
Like, I don't know if I'm right over here, but
Yeah.
would that be considered some sort of continuous symmetry where every single rotation that you make?
No. That is not a degree of freedom. The degree of freedom refers to what? An atom has 3 translational degrees of freedom. Any atom. Now, atoms are connected in the molecule, bonded to each other in the molecule. Therefore, if you assume that the bonds don't exist, the atoms have 3n degrees of freedom, where n is the total number of atoms. But now the atoms are constrained. Constrained in the sense they are bonded. So, now you have to see motion in which the atoms move at the same direction. If all atoms are moving in the same direction with the same velocity, it's possible. Because you have 3n degrees of freedom. You can choose all the atoms to say, now all of you go this way. That's translational degree of freedom in that direction.
Yes, sir.
Okay. Now, if the atoms move in the y direction, that's translational degree. The reason why there are only 3, because we are in 3-dimensional world. There are 3 mutually independent access systems. And also for the molecule, if it is a linear molecule, if it is rotating, the energy change, the system, the rotational motion will have an energy associated with it if there is an I omega square to that. In our perception in spectroscopy and all of the real world, we assume atoms to be point masses. Therefore, if the atoms lie on the line, there is no moment of inertia. If there is no moment of inertia, the rotation does not change the degree of freedom of the molecule, because all atoms are, there's nothing that changes. Therefore, it's not a degree of freedom. So, where do we gain that? We lost one of them. So, where do we gain that? We gain that in the relative motion of the atoms. We see that there is one additional degree of freedom that comes for a linear molecule in vibrations. You don't lose the degree of freedom. You locate the degrees of freedom differently because of the energy constraint. You partition the molecular motion according to the energies. And you will see that the degree of freedom for a linear molecule about its vibration bending in one direction and bending in a plane perpendicular to that another one, they both will have the same energy because the planes are in your mind. The molecule, as far as they are called the degenerate degrees of freedom for carbon dioxide. So you get additional degree of freedom if the molecule is linear. But you lose one rotational degree of freedom under point mass assumption. But if the objects are real size, rotation about this axis is not energy free. There will be energy because objects are there. Mass distribution is outside of the line. There will be a moment of inertia. It will be very small. Therefore, the I omega square will be very small contribution. In point masses, I is 0.
I have a follow-up question.
Yeah.
Say you have a molecule like O2. So for a molecule like that, there is symmetry across every single small rotation you make across this axis, right?
Come again?
So O2, for example, it's a linear molecule, right?
Yeah.
So if you rotate it across its molecular axis, it has symmetry whatever rotation you make, right? So,
Yeah.
So what would that symmetry be called?
Oh, the rotational line.
Yes.
Well, it's called a D. It's called C infinity. By any angle you rotate, the molecule looks to be the same. It's not Cn. It's called the C infinity axis. Okay. About the C infinity axis, there's no energy. Okay. What is n, by the way? What is n? N is nothing but 360. Theta is n. Okay. Now n is 0. Sorry, theta is theta. You call theta is n. Okay. It has to be an integer. So theta can be 30.
Why theta has to be an integer?
Which one? Yeah, seven-fold molecule. Heptagon. How would you define the Cn axis? N is an integer for finite rotations. So see, you need to have atoms which rotate, and replace each other in various locations. Okay? So n is defined by the angle theta, whether it's 60, 90, 120, 180. 180 is the,
All factors of 360 only possible.
they are factors, integer factors, yeah. Now, if the angle can be anything, the n is obviously infinite. Okay? So 360-degree rotation, by any small angle you rotate, you have exactly the same structure, and that small angle can become smaller and smaller. Therefore, it is the infinity axis. Okay?
So, sir, that way, for any molecule like that, you will have infinite elements of symmetry because you will
No.
have. So, because you have one C infinity.
No.
Then C infinity minus.
Oh, yeah. For linear molecules, when there is a C infinity, the number of group elements is infinite. Right? Yes. It's not a finite point group. It's an infinite element point group. Yes, it is. No doubts. Okay. Yeah. Okay. So we'll stop because I think what is important for you is to stick to time and also relax, go back. And I think I'm there tomorrow at the same time, probably 4:30 to 5:30. We'll look at the octahedron possibly, and you'll see some very interesting things. And then in the third lecture, I'll talk about the C60 symmetry elements. Okay. You also go back and look at, go to Google, find out what's the most symmetric molecule, what are its symmetry elements, and try to have some pictures around them. Okay. We'll meet tomorrow. Yeah. Any other question? Yes. Go ahead. Yeah. What about? Yeah. What about the double bonds? What's the question?
You rotate it by a small angle.
Yeah.
What the double bond?
Yeah.
C double bond O is still a double. Oh, okay. Carbon dioxide, if you think about it, we are not talking about the orbitals yet. We are talking about the atoms as point masses. Actually, carbon is double bonded to the oxygen. So, about the double bond, what is meant by a rotation? You assume that the double bond is cylindrical. So, in ethylene, the orbital cloud is cylindrical, right? In acetylene, take acetylene, CH, CCH. There is a C triple bond C. No, but the orbital cloud is cylindrical. Therefore, any rotation is possible, right? So, there you can understand. In that case, you can do that, yes. But otherwise, it's the atoms, point masses that we talk. We don't come to the orbitals. When you come to the orbitals, you are coming to the application of the group to the orbital energies and understanding the orbital behavior and understanding why certain orbital constructions are permitted for reactions, certain orbital constructions are not permitted for reactions. That's called the Woodward-Hoffmann rule. Woodward and Hoffmann rule in organic chemistry. It's very famous for that. Application of symmetry to atomic orbitals of the various atoms.
Excuse me, sir. I have a doubt, sir.
Yeah, just one moment. Yeah, I'll talk to you. Woodward and Hoffmann both won the Nobel Prize, but at different times. Woodward won the Nobel Prize first, 30 years before Hoffmann won the Nobel. 20 years before Hoffmann won the Nobel Prize. But Hoffmann studied the symmetry aspects of organic reactions, and he came up. Raoul Hoffmann is now in Cornell University. Yeah, he's alive. He's in his 80s. He's very well and very articulate. And today morning today afternoon you had Shankar Raman. Shankar Raman's book, he wrote a foreword for him. You should talk to him tomorrow.
Excuse me, sir. I have a doubt, sir. So, sir, what did he mean by inversion symmetry and center of symmetry?
Yeah, inversion symmetry means you have atomic coordinates. Suppose the molecule is in space. You put coordinates to each atom with an axis system.
Yes, sir.
That atom, if you change its coordinates to minus,
Yes, sir.
suppose it's XYZ here,
Yes, sir.
and it's minus XYZ is here. There should be another identical atom there,
Yes, sir. Okay.
because that will go here, this will go here.
Yes.
So in this case, you won't have that.
Yes, sir. Cis
In this case, you will have.
yes, sir. But then what is center of symmetry then, sir?
Okay, the center of symmetry here refers to the point when the dipole moment is zero, about that point, the molecular electric structure. Here, there is no center of symmetry.
Yes,
This
sir.
molecule has a dipole moment. There is no dipole. Here, there is a center of symmetry right here, because the dipoles add up to zero.
Yes, sir.
So we talk about the center of symmetry with respect to the electric dipole moment.
Yes.
Yeah.
And one more thing, And so, somewhere here, solid has translational symmetry,
Okay.
which gives space groups. What
Yeah.
is that, sir? Like,
No, what I'm saying is you take the solid, the lattice points are identical, right?
yes, sir. Lattice in a sense.
So suppose you take a cubic solid,
Yes, sir.
8 atoms are there. But if you extend the cubic solid in space by adding the base units, the lattice vectors, you will see that the lattice is the same irrespective of which point you are in.
I didn't get
No,
this.
suppose you have a lattice structure like this. Okay, they're all identical. So if you have an axis system here, if you translate this axis system to here, will the solid look any different? That's the point. In an infinite dimensional. So when you translate the solid across what are called the lattice vectors A, B, C, every lattice is formed as a combination of A, B, C, NA plus MB. These are called the unit vectors. Okay, and NA plus MB plus maybe LC if you want. Okay, for integer N, M, L, they are identical points, infinite. Therefore, if you move in solid by that one lattice translation, it does not matter whether you are here or you are there. It's an identical. That is called the space translation, and the symmetry is called the space group symmetry. Yeah.
And also, one more thing, so I had so many doubts.
Yeah.
3 translational degrees because X, Y, Z.
Yeah. Yeah.
And also, sir, for linear, the symmetry is C infinity. So let's say I take C like CO2. So
No matter how many degrees you rotate, it's still the same.
degrees. So what if I take a plane perpendicular like
That's a different thing. That's not a C infinity V.
yes, sir.
That's not a C infinity V. That's a C2V if you,
Okay, yes. Sir.
provided the two atoms on both sides of the center are identical.
Yes, sir.
Acetylene, you can do that. But monochloroacetylene, you cannot do that because the chlorine will come here.
Yes,
That's not the same thing. So monochloroacetylene does not have this axis.
So, but on this axis, how is it too, sir? Because we have this one.
So if you have the molecule like this, any axis, this axis, this axis, this axis, you take a plane here, circle here.
Yes, sir.
The axis which is perpendicular is the radius.
Yes, sir.
There are infinite such axes.
Yes, sir.
So there are infinite C2 axes
Yes, sir.
if they are like this.
Okay.
Okay?
I still didn't get this.
Now, if you rotate the molecule, suppose you have an axis here, the rotation is about that axis.
Yes, sir.
Okay? So if you do that, okay?
Oh, infinite. You can do it infinite
Yeah,
times.
that's right.
Yes, sir. Okay.
Because all of them are perpendicular.
Yes, sir.
So you will have infinite C2 axis.
Yes, sir. Okay.
Provided the molecule has a center of symmetry, both sides are identical to that center.
But how is it C2? Because if we rotate it like this, it's also 90.
If you rotate like this, it's a C2, 180 degrees
Okay. Yes, sir. Okay.
about this axis.
Is it necessary that it has to be 180? Can't we take 60, 120?
No. You will not see a linear molecule. If you rotate by 60, you will come to this configuration. That's not spatially identical. Now I know when I look back, I know the molecule has displaced itself.
Yes, sir.
The molecule, if it goes back like this, that will be happening only at 180 degrees.
Yes, sir.
60 degree will bring it somewhere here.
Yes.
90 degree will bring it somewhere here. But that's not the same spatial.
Okay, spatial.
Oh, it has to be spatially identical before and after the rotation.
Yes.
That's the definition of the symmetry element.
Yes.
Yeah.
Thank you, sir.
Okay. Yeah. Okay. Good. Yeah. Yeah.
Reflection and rotation could be combined to form one type of symmetry. Why not inversion and rotation or inversion and reflection?
They will. I'll get to the group the structure.
Then it will be
When
more
you
like
combine inversion with, if the inversion exists and if the rotation also exists, their combination this way or that way will also exist in the molecule. Will also be there. And that's why it is called a group.
rotation of 90 degrees for this molecule doesn't exist,
Yeah.
but in combination with reflection and it does.
Therefore, but remember that reflection is not an element by itself. The rotation is not an element. Therefore, the rotation reflection is a single element. It's not split into two. It's a single element. Whereas on the other hand, you may have a C2 rotation in a molecule, like acetylene, what I have written. Okay? there's an axis, and there's an axis perpendicular, plane of the molecule. The molecular plane is also perpendicular to the C2 axis. Therefore, that molecule has an inversion center, which is a combination of the C2 rotation and the reflection. So, C2 is an element, sigma is an element, therefore their combination is also an element of the group. The group will be defined later, like I didn't define you the group. I said these will obey the group, but exactly what a group is, when I define, you'll see that these things are one-to-one mapping.
If inversion exists and rotation also exists, the combination.
Then their combination, whichever way you do, will also exist in the group. So that it is a closed set of elements. So the set of elements, not only that, if inversion exists, what is the inverse of the inversion? Doing it twice.
The same.
Doing it twice. Suppose you change the coordinates x to minus x and minus x to minus x, minus of minus x, you get to x. So if you do inversion twice, that's equivalent to identity. So the inverse of a rotation is also, inverse of an inversion is also an element. So the moment you define an element, its inverse is defined by that the combination of the two is equal to identity. So C3 and a C3 square. If you take the two of them together, it's a C3 3 times, which is identity. A C3 done twice is the inverse of a C3. They are part of the same group. So we'll see that. We'll see the molecular structure in the process later. Yeah, go ahead. Yeah, go ahead. Yeah, do that. Thank you. We'll continue tomorrow.
So I would like to present my thanks on behalf of the entire class for the fascinating lecture. The relation of the symmetries, which I usually see as an extremely geometrical process in chemistry, was quite refreshing to hear. In conclusion, it was extremely informative and amazing lecture, explained beautifully by Professor Mangala.
Thank you. Yeah.
Swayam Prabha, Digital India, Educated India.